Okay, alô? Mas está saindo na live, tudo bem. Ah, beleza. Eu falo um pouco mais alto. Beleza. Ah, funcionou agora. Hello, everyone. It's a pleasure to introduce Professor Makaiko Chithambo, renowned physicist and head of the physics department at Rhodes University, South Africa. Professor Chithambo holds a BSc from the University of Malawi and MPhil in solid-state physics from the University of Sussex and PhD in solid-state physics from the University of Edinburgh. He is the current president of the South Africa Institute of Physics. Professor Chithambo's research focuses on the study of point defects in materials using the luminescence methods, including thermoluminescence, radioluminescence, and time-resolved optical stimulation techniques. He has authored over 130 publications and the book An Introduction to Time-Resolved Optically Stimulated Luminescence. He has also contributed chapters to the prominent book in this field. We extend our gratitude to Professor Makaiko, to São Paulo Research Foundation for funding Professor Chithambo's visit here, and to the Institute of Physics at the University of São Paulo for their support. Thank you, Professor.
Okay. Todo dia é prazer conhecê-los. Meu português não é bom, mas eu acho que próximo ano eu falo. So thank you very much for the invitation and for the kind introduction. I'm honored to be at the University of Sao Paulo, and thank you also very much to members in the audience for taking time to attend this talk. This is a light-hearted look at my work and also to touch on my home institute, Rhodes University, just to provide some information and some details. So as a way of introduction, I'm just going to skim through issues to do with defects in solids, describe my work, and then give you some information about Rhodes University. Now, when we think of defects in solids, which is the basis of what we do, one can introduce the idea by looking at an ideal periodic structure. Okay? Because the structure is ideal, it's repetitive. Repetitive in 2 dimensions, repetitive in 3 dimensions. But in reality, that's not what we get. And one can think of simple departures from the ideal. For example, you might get a vacancy, a missing atom. You might get an interstitial, an atom at the wrong place, and so on and so on. So because real materials are never ideal, and there will always be some imperfection, some defect, that gives us the basis for our study, for what we do. We can learn lessons from physics, but there's also a lot you can learn from outside physics. And for those of you that do knitting can teach us a lot. So here's a piece of knitting. If you look very closely there, you'll see that there's a hole there. Okay, so maybe during the knitting, someone dropped a stitch, and ended up with a hole. That's a vacancy. Okay, so you might also get another idea, in that perhaps during the knitting you accidentally pull the threads. Okay, and that can define a dislocation line. Okay? So I'm giving these examples simply to say that because this is a structure that's built up, nature built up in some ways, but knitting also tells us that when you build up a structure, you can introduce imperfections or departures, because those type of accidents even occur in nature. Okay. Now, I know that some of you are probably thinking that, oh, where did you get these pictures? Maybe you got them from the internet. I can assure you, I didn't get them from the internet. How do defects come in? What's the nature? What's the origin? Okay, so one can very quickly look at the thermodynamic equilibrium by thinking of entropy. So let's think of a crystal with n ions and n vacancies at a constant pressure and temperature. This is like an n plus n perfect crystal from which the ions have been removed. Now, to minimize, to get thermodynamic equilibrium, the Gibbs free energy of the system must be minimized. Okay? And that's the Gibbs free energy. Okay? And if we do that, thinking of the entropy as configurational entropy, okay, how many ways you can put in the vacancies. If we minimize the entropy, the result is that our small n is equal to some number. That's the important bit. Our small n is not equal to 0, it's equal to some number. So what that is telling us is that the presence of imperfections is necessary for thermodynamic equilibrium. The presence of imperfections is necessary for thermodynamic equilibrium to occur. And so the presence of defects in solids is inevitable. We just can't, we can't escape it. It's inevitable. And defects introduce a lot of desirable properties. So here's an example of copper, for example. If we add tin, a little bit of tin and a little bit of zinc to copper, we get bronze. Copper itself is a very soft metal. You can shape copper, but bronze is a very hard metal. Think of aluminium oxide. You add some chromium and you get ruby. Zoesites that have got some transition metals, vanadium and iron and so on and so forth, you get tanzanite. And this type of minerals have a commercial value, but the commercial value. Okay, so the commercial value that you get in these materials is essentially because of the imperfections in them. Okay, so the perfection has given a body or a use to the material. The electronics industry, cell phones, even our bank cards, they work on the same principle. If you are going to get charge to drift along in a circuit for a cell phone to work, it's because of the presence of imperfections. You can use your card. Hopefully your payment will not be declined, but there we are. Luminescence, so this is now where we work. This is our research. And stimulated luminescence is just a method for sensing changes in point defects. And we can visualize that by giving a very simple example of an anion vacancy. So if you have an anion vacancy, so this is an anion, this is an ionic material. If there's an anion vacancy, okay, that's like a positive neighborhood. And if an electron wanders in the material in that neighborhood, is going to get trapped in place. Okay? And because this is like a potential well, it's going to have some energy levels, and the relaxations then will give off a signal that you detect as luminescence. So one can define luminescence as the emission of light from a previously irradiated material or semiconductor when it is heated at a controlled rate or when it's exposed to light of certain wavelengths. You can illustrate that using a conduction band where the energy levels are separated by a band gap, and the defects within the material, they provide electron traps and recombination centers, so that when you ionize the material, some of the free electrons can get trapped. They can end up at your electron traps, and when you stimulate, you release some of those charges, and their recombination then gives off the signal that you measure as luminescence. Okay, so again, we're just exploiting the fact that the material has defects in it that you can adapt and use for whatever need. There are different types of luminescence. There's optically stimulated luminescence, in which your signal simply decays in time. You have linearly modulated luminescence, in which the signal goes through peaks. Okay, so each one of those peaks showing the release of electrons from a particular electron trap. Okay. Let me just talk a little bit more about thermoluminescence, which is a method of sensing changes in concentration of defects as you heat the material. Okay. What you get is a collection of peaks, and each one of those peaks, it simply signifies the presence of an electron trapping defect. This is an example from aluminum oxide, okay, which is a dosimeter. And that's the emission spectrum we measure. So the glow curve, this one shows peaks, and each one of those peaks is a pointer to the presence of an electron trapping defect. A spectrum, an emission, is a pointer to the presence of a defect at which the radiative recombinations take place. With aluminium oxide, this particular example, you've got a large collection of color centers, which are just oxygen vacancies that have trapped electrons. And measurements like that will show the dominant emissions, but in truth, there is more. There are more emission bands. So what I've listed there is more of them. The point here is that we can do measurements. Yes, we do measurements, but our measurements are not necessarily exhaustive. Okay? Our measurements are not necessarily exhaustive. They will, in most part, depend on the equipment, how good the equipment is, but they'll also depend on empiricism, in detecting very, very weak but important signals. So, if you do that, you can work out a scheme. You can work out a scheme of your emissions, and in this example, so this is aluminium oxide again. This bit here is showing what happens at the F center. Okay. So you have this bit here on the left. You have an electron trapped at an F plus center. An F plus center is just an oxygen vacancy with a single trapped electron. Okay, so electron trapped, it creates an excited F center. Then that excited F center then relaxes with the emission of light from the 3p to the 1s ground state. Okay? And obviously, you do also get aggregates. Okay, you do get aggregates, and some of those aggregates are also responsible for the emissions that you get. This type of information is, you can do that if you are able to measure your glow caves and emission spectra as well, and then understand the physics of the defects in your material. Another method of doing this is to measure what is called the time-resolved luminescence. Okay? Time-resolved luminescence is a measurement that you do when you separate in time the emission and the stimulation of the luminescence. Okay? Why do you do that? It's because you want to study the dynamics of the luminescence. Okay? So, in principle, you stimulate a photon, and then you measure the delay between the start and the stop, or between the stimulation and the emission. That delay is a lifetime. And those lifetimes, the components of the lifetime, it consists of the time it takes to detrap an electron from a trap, the time it takes to transit through the conduction band, the time it takes to recombine through excited states at the recombination center. So in that way, then you can study the dynamics of the process in your material. That's the aim of this method. Here's an example of a spectrum, and you can see in this spectrum that we have calculated some lifetimes. Those lifetimes give us some information that we can use to explain radiative and non-radiative processes in our materials. I'm not going to go through the details of this, but this is an example of configurational coordinate diagrams telling us that we are looking at probabilistic events. Okay, so because the nature of recombination events are probabilistic, consisting of radiative terms, consisting of phonon-assisted terms, consisting of non-radiative terms, this gives us a way to look at various things. What is the effect of temperature on our material? How does radiation affect it? Can you use that for provenance and various other applications like dosimetry and so on and so forth? Okay. Here's an example of the dependence of lifetimes on luminescence intensity. This Colóquio here is, I showed this earlier. This is the same material. You can see that one of them has one peak, the other one has two peaks. Okay? If you measure the lifetimes from these materials, it's mirrored. Okay? The one with a peak at a lower temperature also gives you a peak in the lifetimes. Okay? It also gives you a peak in the lifetimes. So, which is the point I made, that you are looking at the dynamics of the recombination. So if you have an electron trap, that electron trap would tend to retain your electrons. Okay? Because what you are doing really is trying to give energy to your material so that the trapped electrons can overcome the potential. Okay? They can overcome the potential. And if it takes longer to release your material, then the time-resolved measurement is going to measure that lifetime. And what we see here is that indeed, for this sample that without a single, without a shallow trap, you see that it's flat. The one with a shallow trap, it goes through a peak. Okay. So you can modify the band. You can use that information to modify the band model of your material. Again, this is just an attempt at that. Okay, let's not look too much into the detail. Another method is phototransferred thermoluminescence, and phototransferred thermoluminescence arises at one electron trap because of a light-induced transfer from another. Okay, so if you have a trap that is at a deeper, okay, with a very high activation energy, you can move electrons to one with a lower activation energy. In that way, study the properties of your electron traps or your defects in your material. Okay, so the process is to irradiate the material and then to preheat it in order to deplete some of those traps. Then you illuminate it to induce phototransfer, and then do a measurement. Okay, so here is a diagram that attempts to explain that. Okay, so you have electron traps within the band gap. You have light stimulating, then you have your signal showing a release of the electrons. Okay, so this one is an example of a measurement of a Colóquio from beryllium oxide. Beryllium oxide is a dosimetry material. Okay, so we have peaks here that are reproduced for phototransfer. Okay, so we cleared them and we reproduced them by phototransfer. This is one way to study. Very deep electron traps in materials, because with a Colóquio like this, we obtain the signal by heating it. Okay, maybe room temperature to 500, but some of the very deep electron traps are accessible at, let's say, 800 or 900 degrees. There's no system to do that. So you do it indirectly, okay, which is what you do with phototransfer. You can mathematically model the process using various methods. So a phenomenological model in which you can write the transport of electrons as a family of differential equations, which is the matrix on the left. Or you can use simulations, mathematical simulations, to get a numerical solution, okay, which is the example on the right. So these are just examples of those type of attempts. This one here on the left, that's your data described by a phenomenological model. The one on the right, that's the same data described by numerical simulation. Okay, so what's the difference? In the phenomenological model, we accept our limitations and our problems. So we introduce simplifications in the mathematics. Okay, we introduce all kinds of simplifications. With the numerical solutions, we try and describe the system without any simplifications. Okay? That's the difference there. So in summary, the objectives of our research is to understand the physics involved, and the study of defects is an essential element of modern solid-state physics, and that's something that we have to do. It also helps to refine applications, because if you understand the role and the type and the physics of your luminescence and how it comes out, then the applications can be properly refined. You get ideas for new applications. Okay? So it's not just a paradigm that you follow. The work that you do, you are able to spawn and generate new ideas. Many applications that you can do. An interesting one is from arthroplasty. So in arthroplasty, it uses ultra-high molecular weight polyethylene, which is a polymer. And this polymer has linear and branched molecules. And because of that advantage, it's highly resistant to impact and wear. Okay? The only problem is that before use, before implanting in the body, it's sterilized by electron beams or gamma irradiation, which is high energy radiation, and it tends to sever. It tends to sever and cleave the bonds, the carbon-hydrogen bonds, which is a cause of wear. It makes it wear. So from studies of the luminescence of the materials, we determined that one of the causes is that the severing or cleaving of the bonds creates free radicals, which are very reactive and very bad for wear and resistance of the material. So if you have a kneecap that's replaced by arthroplasty, you don't want to go through that every 2 years. Okay, so which means that you want to use methods that avoid that, like using ethylene oxide or some type of gas. Okay. Then something that's of interest is the illicit trade in gemstones, or at least of interest to me. Because you might have read in the news that there are what are called blood diamonds. All kinds of wars, people invading places and killing people because they want to mine the diamonds. They want to mine the gemstones. So you have this type of trade where people are just beyond reach of government and the importance of government. And I think the United Nations and other organizations have declared such gemstones, such diamonds as blood diamonds. the question is if that goes on the market, how can you identify it? Okay, it's very difficult. But in truth, with luminescence, you can get a signature, because the origin of materials will usually depend on the origin. So if you can measure a spectrum, maybe a Colóquio or something, that is characteristic of the origin, you can more or less guess that, okay, this is a genuine trade gemstone or genuine trade diamond. This one is a blood diamond. Okay, so you can control that type of trade by actually looking at the physical properties of the materials. Okay. Of course, you might want to use other methods. So that I think would be is an interesting application. And then there's also luminescence dating. Okay, to work out how old materials are. You work out an age by using that expression. I don't want to say too much here because Professor Chubachi is here. If I make a mistake, he will arrest me. So anyway, if you can date your material, then you can tell the difference between which piece is genuine, which piece is a copy. Again, because on the market you are likely to get cheats. You know, people passing off some material and saying, "Oh, this is from the 14th century," and so on and so forth. Okay. So with this material, I mean, with this method, you can date those materials and sort out that problem. Okay. There's also a space dosimetry, because in space, you know, you are exposed to all kinds of radiation fields, and if we know the properties of our materials, if we can work out what's the effect of radiation on them, then you can work out how to better refine the materials that are worn by astronauts or that are used in space flight to protect the astronauts from the radiation fields that you get in space. So those are just selected applications. My own work is based mainly on understanding the physics of the defects, but the colleagues I work with, you know, Professor Nero, he also combines applications as well. So which for me is an honor to work with Professor Nero and his students at University of Sao Paulo. Okay, then finally Rhodes University. So that's my university. That's where I come from. Rhodes University was founded in 1904, which makes it 120 years this year. Okay, so I'm told it's older than University of Sao Paulo. Yeah, but it's not as big. In fact, it's the smallest university in South Africa. So it's a public research university in the Eastern Cape. This is the Eastern Cape here, where I've showed the arrow. It's a public research university, which means we receive most of our funding from government. Okay. We have 6 faculties. The oldest one is humanities. Those are the faculties: humanities, commerce, law, science, education, and pharmacy. And the faculties are subdivided into 30 departments. 10,000 students, which is a tenth, I think, of University of Sao Paulo. 60% of the student population is female, 40% is male. We do get a lot of international students as well. from all over Africa, okay, and others from all over different parts of the world. So the need for collaboration is that, you know, we need to foster mutually beneficial research partnerships with the University of Sao Paulo. It's always a benefit for me to be here, to learn new things, to know what's going on, to get some samples from Minas Gerais, and also to learn and benefit from the very strong research establishments of the University of Sao Paulo. You know, although our university is older, some of the research establishments I've seen here are very, very strong. Very, very strong. So there's a lot that we can learn and pass on to our students as well. Hopefully we can form programs that for student staff exchange, for research skills development, you know, research skills development, particularly now where Brazil and South Africa are part of the BRICS establishment. So it's in our benefit at Rhodes University to leverage that for skills development for the benefit of our students, and hopefully also for the benefit of students in Brazil. That's one thing. This is my first visit to Sao Paulo. So I'm thinking in my mind, you know, what should I take away, you know, when I go back? Anyway, so that's Sao Paulo. I think so. And my friend Nero tells me it takes him 1.5 hours to get to work. Then I told him that it takes me 5 minutes to get to work, and he was surprised. This is why. Thank you very much.
Questions? Some question?
Thank you, Makaiko, for the presentation. Sorry for the air, the sound. Sorry for that. But anyway, I was curious about the finding illicit traffic of gemstones. You talked about TL being a signature, but depending on the heat treatment or the irradiation, can this be a disguise, and you cannot ideally check if the gemstone is or not from a determined region? Do you check for the wavelengths of emission, peak position? What are the measurements that are made to check if they are from one region or another?
Yeah, so it would have to be a combination of everything. The natural TL will often be similar. Once you irradiate it, you're going to induce peaks. So if your natural TL will give you a certain behavior, like we see in quartz, that we have a peak at a high temperature, not at the low temperature, at a particular position, depending on the heating rate. You have a wavelength of emission in the UV, near the UV, and so on and so forth. Then combined with things like maybe X-ray diffraction and other methods, so you try and get a body of information to say, in general, if this material, if this type of quartz comes from this geology or this area, it will generally have this type of property. And then the artificial treatment, you might say, what does the artificial treatment do to it? And is that process reproducible? So what you want to look for yeah, the signatures are something that's unique. Yeah.
More questions? Some more questions? Professor Chithambo, Professor Luis Jacobson is in Zoom, and the Professor Jacobson from United States, and it's a pleasure to see Professor Makaiko and Professor Elizabeth, and I sent my regards to them. Okay.
Okay. Thank you. Thank you very much.
Some question? No. I'd like to see a little bit more about what are the difference for you when to study minerals or to study synthetic materials? What is the big difference for you and to study in your study?
Yeah, for me, I think studying synthetic materials they can be predictable. Well, not predictable, but well behaved. So usually the intensities are high, you get peaks in nice peak positions, they are reproducible, very nice to study. Natural materials, you have to be lucky, and there's a challenge there. Sometimes you get materials that are very weak, okay, but interesting. So I gave, for example, the example of tanzanite. Tanzanite is a natural gem mineral, which makes it interesting to study because it's rare and it's found only at one place in the whole world, okay, in Mererani in Tanzania. The problem is that it's very weak. It gives off very, very weak signals, which means you have to do all kinds of things. Natural materials also tend to have admixtures. So like quartz mixed with feldspar, then what do? You know, how do you study it? You do all kinds of chemistry to separate it. What if it's in a mineral form? Sometimes natural minerals, like alexandrite that Alexia studied, you look at the phototransfer. You get a phototransfer, but you get sometimes signals that don't follow your theory. You know, they don't come down, they just keep increasing. Then there's also this question of sensitivity change. Okay, you measure the material, it becomes more sensitive. You measure the material, it becomes more sensitive. And of course, for the purposes of research, I think it's interesting because it gives you something to do. But in my opinion, natural materials are a challenge. And you know, I respect a lot people who study natural materials, whether for dating or other uses. If I had a choice, I would like to study synthetic materials.
Perfect. I have some question, Professor Jacobson again. In one of your slides, you say that the thermoluminescence measures the change in the concentration of defects. I think you mean it changes the concentration of populated defects since the traps remain in the material after the measurement. Could you comment?
Yeah, I mean, semantics, it's true. Yeah, so what you are sensing is that you have a defect that's able to retain electrons. For example, you hit it, you clear. So by clearing, you are clearing the concentration of trapped electrons. So to be more accurate, we can put it like that. That it's you are sensing the clearing of trapped itinerant electrons at defects in the material. you don't actually remove the defects themselves. So that's correct, yes.
Perfect. Some question? It's okay? Thanks so much, Professor Chithambo, again.
Okay, thank you. Thank you.